Welcome to Jeremy's IT Lab. This is a complete course for the CCNP ENCOR, Enterprise Core exam. This course will cover all topics you need to know to pass the ENCOR exam. This video is the first video of the Spanning Tree Protocol section of the course. We'll cover classic STP, which is IEEE 802.1d, and then in future videos proceed to cover RSTP, which is Rapid STP, and MSTP, which is Multiple STP. Here's what we'll cover in this video. First, we'll briefly review why STP is needed, and then we'll walk through the STP algorithm, how the root bridge and the various port roles are selected, root, designated, and non-designated. In the following videos, we'll go more in-depth into other aspects of STP, but in this video, we'll just focus on the algorithm used to select port roles. Let's get started. First up, what is the need for STP? In a LAN with redundant connections, meaning there is more than one possible path to reach a destination, the flooding of BUM traffic, broadcast, unknown unicast, and multicast frames, will result in loops. It's inevitable. And unlike the IP header, the Ethernet header has no field to prevent a message from looping indefinitely. If enough looping frames accumulate, the result is a broadcast storm, meaning the looping frames take up so many network resources, such as interface bandwidth, that the LAN becomes unusable. A broadcast storm can take a network down in a matter of seconds, so loops must be avoided. You can't have a functioning LAN with a layer 2 loop. For example, if this PC sends a broadcast frame, it is flooded. Then, each switch that receives the frame floods it, and it repeats and repeats indefinitely until the LAN goes down. Each time the frame is flooded, it multiplies. I haven't shown all the arrows here. It would be even more of a mess than this, but a single broadcast frame will soon multiply and become a big problem. So, what does STP do? How does it prevent layer 2 loops? STP, originally standardized in IEEE 802.1d, prevents layer 2 loops by disabling redundant links. Here's an example LAN with many redundant links. This LAN is certainly resistant to hardware failures, but without STP, a single broadcast frame would soon multiply and take down the LAN. With STP, redundant links can be disabled, leaving only a single active path between any two destinations in the LAN. This is a loop-free topology. A spanning tree is a concept in the mathematical field of graph theory. In graph theory, a graph is a structure that models relationships between objects, also called nodes. A tree is a subgraph, in which any two nodes are connected by exactly one path. And spanning means that the tree includes all nodes. The tree spans across all nodes. That's where the name Spanning Tree Protocol comes from. The physical topology on the left can be considered a graph, with various connections between nodes. The logical topology on the right is a tree, a subgraph in which any two nodes are connected by exactly one path. And the tree spans across all switches in the LAN. It is a spanning tree. Now let's see in more detail how Spanning Tree Protocol creates a spanning tree among the switches in a LAN. The process STP uses to create a loop-free topology is called the STP Algorithm. Here's a summary of it. There are three main steps. First is the root bridge election. One will be selected for the LAN. Or I should say one per VLAN, because Cisco switches use per VLAN spanning tree protocol, which creates a separate spanning tree instance per VLAN. The switch with the lowest bridge ID will become the root bridge. Keep in mind that STP was developed before switches, so STP uses the term bridge. Bridges can be thought of as predecessors to switches, but in the context of STP, a bridge and a switch are the same thing. Even the latest version of the standard uses the term bridge, even though bridges have been replaced by switches. The next step is the root port selection. Each switch selects one, and it is selected using the following parameters: lowest root cost, lowest neighbor bridge ID, lowest neighbor port ID, and finally the lowest local port ID. We'll see where that last one comes into play. And the final step is designated port selection. One is selected per segment. In this context, a segment means a collision domain. The parameters used to select it are the port on the switch with the lowest root cost, the port on the switch with the lowest bridge ID, and finally the lowest local port ID. And then the remaining ports are non-designated. Here's the network we'll be using for this lesson. If you want, feel free to pause the video here and figure out the STP topology yourself. Identify the root bridge, root ports, designated ports, and non-designated ports. Now let's walk through the STP algorithm. Because most of this is review from the CCNA, I'll go through it fairly quickly. First up, the root bridge election. Switches will communicate with each other to elect a single root bridge for the LAN. Actually, with Cisco's PVST+, there will be a root bridge for each VLAN, but we'll focus on a single VLAN topology for this video. The root bridge serves as the central point of reference for the spanning tree. Then, other switches will ensure that they have exactly one active path to reach the root bridge. Other redundant paths should be disabled. To elect the root bridge, switches will send BPDUs to each other, and the switch with the lowest bridge ID becomes the root. Note that only the root bridge generates new BPDUs, and then other switches will forward them out of their designated ports. However, after booting up, each switch believes it is the root bridge. Therefore, it sends BPDUs out of all ports. So, assuming these 4 switches booted up simultaneously, they will all send BPDUs like this. In each switch's BPDUs, it states its own bridge ID, as well as the bridge ID of the switch it believes is the root bridge. At this point, each switch believes it is the root bridge, so the my bridge ID and root bridge ID values are the same. Let's examine the contents of the bridge ID. It is a 64-bit number divided into 2 parts, a 16-bit bridge priority and a 48-bit MAC address. Then, the bridge priority is divided into 2 further parts, a configurable priority value and the VLAN ID of the STP instance. As for the MAC address, it is not a MAC of any particular interface, but rather a MAC that identifies the switch as a whole. The easiest way to view this MAC address is to use the show spanning tree command. Note that Cisco switches run a proprietary version of STP called per VLAN spanning tree plus, PVST+. PVST+ runs a separate STP instance for each VLAN, which allows traffic in different VLANs to use different links, avoiding congestion. In this video, we'll just focus on a single STP instance, VLAN 1, but in a future video, I'll talk about load balancing with STP. Anyway, the default priority value is 32768, with the most significant bit of the priority field set to 1. Note that only the most significant 4 bits of the entire 16-bit bridge priority field can be configured. The other 12 are reserved for the VLAN ID. For that reason, the priority value can be modified only in increments of 4096, because that is the value of the least significant of the 4 bits. Then, the extended system ID, the VLAN ID, is added to the priority value to make the switch's total bridge priority. So, by default, a switch's bridge priority in VLAN 1 will be 32769, 32768 plus 1. What is the point of adding the VLAN ID to the priority? Well, the STP standard mandates that each switch must have a unique bridge ID. Each VLAN on a switch operates like a standalone virtual switch, sending its own spanning tree BPDUs. So, to comply with the standard, that VLAN ID is added to the priority, ensuring that each virtual switch has a unique bridge priority, and therefore a unique bridge ID. So, after exchanging BPDUs with each other, all switches agree that switch 3 is the root bridge. It has the lowest bridge ID because it has the lowest bridge priority, 1. Actually, that's 0 plus 1. The priority value is 0, and the VLAN ID is 1. And here are switch 3's port roles. Normally, all ports on the root bridge are designated. However, in this case, G00 and G01 are connected to the same segment, the same collision domain. So one will be designated and the other non-designated. Switch 3's G00 becomes the designated port because it has a lower port ID. As I'll mention later, that's the final tiebreaker in the designated port selection process. Honestly, I doubt you'll encounter questions involving hubs on the ENCOR exam, but just in case, I want to demonstrate how the designated port is selected in such a case. So, after the root bridge election, each non-root switch will select exactly one port to be its root port. The root port is a forwarding port that points toward the root bridge. It's the port that provides the switch's single path to the root bridge. The selection criteria are, in order of priority, the lowest root cost, lowest neighbor bridge ID, lowest neighbor port ID, and finally the lowest local port ID. First, we'll look at root cost, the cumulative cost to reach the root bridge via the port. By cumulative, I mean it's not the cost of the individual port itself, but the cumulative cost of the whole path to the root bridge. So how does a switch calculate a port's root cost? When the root bridge sends BPDUs, it specifies a root cost of 0. It is the root bridge, so its cost to reach itself is 0. Then, when a switch receives a BPDU, it adds the cost of the receiving port to the BPDU, and then forwards it. So switch 3, the root bridge, sends BPDUs with a cost of 0. Then, switch 1 and switch 4 each add a cost of 4 for their gigabit Ethernet ports to the BPDUs they send. Switch 1 receives BPDUs from the root bridge on G00 and G01, and switch 4 receives them on its G00 port. So they send BPDUs with a cost of 4. Switch 2 receives those BPDUs and adds a cost of 4 once again, so it sends BPDUs with a cost of 8. Although, once the network has converged, switch 2 won't actually have any designated ports to forward BPDUs out of, so it won't send BPDUs. But right now, we're talking about while the network is converging, before all of the port roles have been decided. As the switches decide their own role, meaning root or non-root, and the roles of their ports, meaning root, designated or non-designated, some ports will stop forwarding BPDUs. For review, here is the STP cost of each port type. 10 meg ports have a cost of 100, 100 meg ports have a cost of 19, 1 gig ports have a cost of 4, and 10 gig ports have a cost of 2. In the topology we're using for this lesson, all ports are 1 gig, so they all have a cost of 4. Note that a port's STP cost is derived from the interface's bandwidth value. This value matches the interface speed by default, but can be configured separately. Just note that the speed command is configured in megabits per second, or depending on the switch you can enter 1G, 10G, etc. The bandwidth command, however, is configured in kilobits per second. The bandwidth value doesn't actually affect the port's operating speed, but influences cost calculations for STP, OSPF, etc. However, a more practical way to modify a port's cost is the spanning tree VLAN cost command. We'll talk more about that in the STP tuning video. So let's see how each switch decides its root port. The first criteria is the lowest root cost. Remember, there is only one root port allowed per switch. First up, switch 1. On G00, it has a root cost of 4. 0, which it learned from switch 3, plus 4 for G00 itself. The root cost via G01 is 4 as well. G02's root cost is 8, 4 from switch 4, plus 4 for G02 itself. And G03's root cost is 12, 8 which it learned from switch 2, plus 4 for G03. So G00 and G01 are tied. Switch 1 can't select a root port yet. Switch 2 is simple. Its root cost is 8 via all ports. It receives BPDUs with a root cost of 4, and then adds 4 for each interface. So all of switch 3's ports are tied. It can't select a root port yet either. And here is switch 4's root cost via each port. Of course, G00 has the lowest root cost, since it's directly connected to the root bridge. Therefore, switch 4 selects G00 as its root port. As for switch 1 and switch 2, we have to proceed to the first tiebreaker. The first tiebreaker is the lowest neighbor ID. The port connected to the neighbor with the lowest bridge ID will become the root port. Switch 1's tied ports were G00 and G01, and as you can see, they are both connected to the same neighbor, switch 3, and therefore they are tied once again. Switch 1 still can't select a root port. How about switch 2? Its G00 and G01 ports are connected to switch 4, and G02 to switch 1. Switch 4 has a lower bridge ID than switch 1, so G02 is out. That means G00 and G01 remain, both tied. So, like switch 1, switch 2 can't select a root port yet either. It has to proceed to the next tiebreaker. If there is a tie for root cost and neighbor bridge ID, the port connected to the neighbor's port with the lowest port ID will become the root port. Note that we're comparing the neighbor's port IDs here, not the local port IDs. Like a switch's bridge ID, a port's port ID consists of two parts: a configurable priority, which is 128 by default, and a sequential number. For example, G00's port ID would be 128.1, G01's 128.2, G02's 128.3, etc. With the default port priorities, you can just compare the port names. For example, G00 is lower than G01, so G00 is superior. Now let's compare neighbor port IDs on switch 1 and switch 2. Switch 1's G00 and G01 ports both receive BPDUs from switch 3 G00, with a port ID of 128.1. So we have a tie. Switch 1 still can't select a root port. As for switch 2, G00 is connected to switch 4 G03, with port ID 128.4, and switch 2 G01 is connected to switch 4 G02, with port ID 128.3. Because G01 is connected to a lower neighbor port ID, switch 2 selects G01 as its root port. That means that switch 4 G02 must be a designated port. The port connected to a root port must be designated, because there must be one designated port per segment. So if one side is root, the other must be designated. Okay, now let's move on to the final tiebreaker for switch 1. If there is a tie for root cost, neighbor bridge ID, and neighbor port ID, the port with the lowest port ID will become the root port. However, this only occurs if two or more ports are connected to the same segment, for example with a hub. It's probably not something you'll encounter, but I think it's good to at least know what happens in such a case. Switch 1 G00 has a lower port ID than switch 1 G01, so G00 becomes switch 1's root port. Also, G01 becomes non-designated. Remember, a switch can only have one root port, and there can only be one designated port per segment, and that is switch 3 G00. Therefore, switch 1 G01 must be non-designated. Note that in RSTP, switch 1 G01 would be an alternate port, and switch 3 G01 would be a backup port. You can confirm that in the CLI. In switches that support RSTP, which is all modern switches, RSTP terminology is used in the CLI, even in classic STP mode. As you can see here, switch 1 G01 is listed as alternate, and switch 3 G01 as backup. I will cover the alternate and backup port roles more in the rapid spanning tree section of the course, so for now, I'm just calling them non-designated. After each switch has selected a root port, each remaining segment must have one designated port, and the remaining ports are non-designated. The selection criteria to determine which port on a segment becomes designated are as follows. First, the port on the switch with the lowest root cost will become designated. If the switches have the same root cost, the port on the switch with the lowest bridge ID will become designated. If multiple ports on the segment are on the same switch, the port with the lowest port ID will become designated. We saw an example of this on switch 3. It is the root bridge, so usually all ports are designated. However, both switch 3 G00 and G01 are connected to the same segment. So only one of them became designated, the one with the lowest port ID, G00. I'll say it once more, you probably won't encounter any questions with hubs on the ENCOR exam, but for the sake of being thorough, I included this hub here. Okay, the remaining segments are the switch 1 G03 to switch 2 G02 link, the switch 1 G02 to switch 4 G01 link, and the switch 2 G00 to switch 4 G03 link. Let's see which ports become designated. First up, the port on the switch with the lowest root cost will become designated. Note that it is not the port with the lowest root cost will become designated. We are comparing the root costs of the switches via their root ports, not the root cost of each individual port on the link. For example, for the switch 1 G03 to switch 2 G02 link, we should compare switch 1's root cost out of its root port, G00, to switch 2's root cost out of its root port, G01. So switch 1's root cost is 4, and switch 2's root cost is 8. Switch 1's root cost is lower, so switch 1's side of the connection becomes designated, and switch 2's side of the connection becomes non-designated. Same deal for the switch 2 G00 to switch 4 G03 link. Switch 4's root cost is lower than switch 2's, so switch 4's side of the connection becomes designated. Finally, there is the link between switch 1 and switch 4. Both switches have the same root cost, so we have a tie. To decide which side of the link will become designated, we need a tiebreaker. If both switches have the same root cost, the port on the switch with the lowest bridge ID will become designated. So here are switch 1 and switch 4's bridge IDs. Switch 4's is lower, so switch 4 G01 becomes designated, and switch 1 G02 becomes non-designated. And that's it. We have now identified the role of every port in the LAN. Just to confirm, here is some partial output of show spanning tree on each switch. If you want to pause and confirm, feel free to do so. Just remember that non-designated ports are shown as alternate and backup in the output. Here's what we covered in this video. First, we briefly reviewed the need for STP to prevent layer 2 loops in LANs with redundant connections. Then, we reviewed the STP algorithm, which I have summarized here. In the following videos of this section, we'll dig into more details about modifying settings to change the STP topology, using optional features from the STP toolkit, etc. Now let's go on to a quiz to test your understanding. Just one question today. Identify the root bridge and the role of each port in the network below. Pause the video now to find the answers. Okay, let's do a quick walkthrough of the logic to check the answer. First of all, switch 2 is the root bridge because it has the lowest bridge ID. This time, all 4 switches have the default priority of 32768 plus 1 for VLAN 1, but switch 2 has the lowest MAC address. Next up, root ports. Switch 1 G00 is its root port because, although its root cost, neighbor bridge ID, and neighbor port ID are tied with G01, G00 has the lower port ID. G02 is switch 2's root port because it has the lowest root cost. And switch 4 G02 is a root port because, although it has the same root cost and neighbor bridge ID as G03, G02 has the lowest neighbor port ID. Next up, designated ports. First of all ports on switch 2 are designated, so all ports connected to switch 2 that aren't root ports are non-designated. Remember, there must be exactly one designated port per segment. Then, switch 4 G00 is designated because switch 3 G02 is a root port. Finally, all that's left is the switch 1 G00 and G01 to switch 3 G00 and G01 segment. Switch 3 has a lower root cost, 8, than switch 1's root cost of 12, so one of switch 3's ports will become designated. Switch 3 G00 has a lower port ID than switch 3 G01, so G00 becomes designated. And finally, switch 1 G01 and switch 3 G01 become non-designated. Okay, that's all for the quiz and this video. I hope it was helpful. Thanks for watching. Before finishing this video, let me thank my JCNP level channel members. To become a member, please click the Join button under the video. Thanks to Yonatan Makara, Velva Jacob, Funny Dart, Nasir Chowdhury, Devin Suku, Gustavo B.R., Marcel Lord, Pavel M., Mr. Erlison, Dragos Hirnea, Zakib Shah, Mayor Salman, Mason Anderson, Vitaus194, Gina Lindley, Mark Jackson, Bold 1C1U, Michael Carroll, Gerald Guillaume, Gabriel Braga, Hector Hernandez, Maratuba, Roji Kuriakos, Arpad Konives, 5 Feet, Owad, Daniel Brown, Tricky Mickey 123456, Scott Thompson, Jose Alvarez, Hussein Yavuz, Kevin Hayes, Samuel Tavares, Roger Bratseth, Mustafa Ersoy, Nasser Zahar, Brian Grant, Georgi Gemejev, Arlen Plagaria, Dear Diso, Adelson Pereira, Farad69, Lucien Stoichitoyu, Madmark50484, Sean Powell, Alexandru Stratan, Hiago Bicalho, Abdo Zizo, Piotr Kaimov, DMJ2, Kurt Nell, Preeti Dongave, Abubakar Berry, Omid Farakesh, Steve Cox, Jasper Yim, Wilmer Romero, Enigma G, Laurent Lam, Emmanuel Nupsido, Pedro Hartman, Ivano Capuano, Jefferson Steelflex, Sinan Sarisinar, Karamjit Singh, Alejandro Okana, Burrell Campbell, Abhishek Sahu, Toxic, Gio, Daniel Andrade, and Vijay Kumar Pili. Sorry if I pronounced your name incorrectly, but thank you so much for your support. Thanks to you and my other supporters, I am able to make these videos and release them for free on YouTube, so I really appreciate the support. Another great way to support the channel is to like the video, leave a comment, subscribe, and most importantly, share this video with others. So if this video was helpful, I'd appreciate it if you did any of those. Thanks for watching.